Campus Talks, diesmal von der Nobelpreisträgertagung in Lindau. Neben vielen Laureaten sind hier jedes Jahr auch Nachwuchswissenschaftler aus aller Welt zu Gast. Einige von ihnen werden gleich über ihre zukunftsweisende Forschung sprechen. Und zwar ohne PowerPoint und Manuskript. Die Amerikanerin Naomi Mburu erläutert, wie Sensoren Organtransporte erleichtern können. Der Ire Philip Lewis erforscht, wie sich der Lichtwechsel bei der Geburt auf die spätere Gesundheit auswirkt. Die Australierin Amy Shepherd versucht, die Alzheimer-Krankheit besser zu verstehen. Haitham Al-Marouki aus dem Oman arbeitet an Verfahren für die Diagnose der Augenkrankheit Keratokonus. Und die Amerikanerin Miriam van Dijk untersucht, was die Häufigkeit von Herzkrankheiten mit der sozialen Klasse und dem Wohnort zu tun hat.
Welcome to Campus Talks and welcome to a very special edition of Campus Talks. We're here in Lindau at the Nobel Prize Winners Conference, but it also brings together young, talented researchers. And 5 of these young scientists now will talk about their work. And the first of our speakers is Naomi Mburu. Naomi comes from Maryland in the United States, but she's on her way to do a PhD in Oxford. The title of her talk is How Sensors Can Improve the Transportation of Organs. And please welcome Naomi on stage.
Hello, everybody. I'm excited to be here to discuss my research, which is focusing on extending the lifetime of organs in transit for organ transplantation. Organ transplants have the ability to save the lives of those suffering from organ failure by simply replacing the organ that has failed with a healthy organ. So what exactly is an organ? Well, the term organ encompasses everything from your heart, your liver, your lungs, even your arms and your legs can be considered to be organs. Currently in Germany, there are over 10,000 people on the organ donor wait list. However, the number of people who are willing to donate an organ is steadily decreasing. Even when an organ has been donated, oftentimes the organ fails due to lack of accessible technology in place to transport the organ as it's being donated. And this is where my research really comes in. So the amount of time that an organ can exist outside of the body depends greatly on the kind of organ that we're considering. For example, your heart can last up to 6 hours outside of the body. Your liver can last up to 40 hours outside of the body, and your hand can last up to 13 hours outside of the body. Currently, when an organ is in transit, it's placed in a container with organ preservation fluid. However, my research group is focusing on trying to revolutionize this process by making a more accessible organ transplantation box that will allow us to measure the concentration of 2 important chemicals present within the organ, while also actively treating these chemical levels so that we can increase the amount of time that an organ can exist outside of the body. The overall goal of our research is to double or even triple the amount of time that an organ can exist outside of the body. And the 2 chemicals that we are focusing on are glucose and lactate. Glucose is a chemical associated with sugar in the blood, and in the presence of oxygen, glucose is converted into energy. However, when an organ is removed from the body, the glucose levels increase because there's no more oxygen being supplied to the organ to convert this glucose into energy. Lactate is a molecule associated with exercise or motion. So when an organ is removed from the body, the organ must work harder than normal in order to try to keep itself alive. And this causes the lactate levels to increase. Overall, the increase in these glucose levels and this lactate levels causes the organ to fail. So we want to be able to monitor the increase in these levels and actively treat these increases. The cool thing about the organ preservation system that my group is working on is that it is self-powered, meaning no external battery source is required. This is really useful in areas such as on the battlefield, where access to batteries is scarce. However, soldiers are very prone to losing organs on the battlefield. So how do we make our system self-powered? Well, we are able to convert a small amount of the glucose and lactate present in our organ into electricity. Some of this electricity goes into sending a signal to a circuit which will let the user know how much glucose or lactate is present in the organ by looking at a monitor or a smart device. Our studies have shown that the concentration of glucose or lactate present within your organ is actually directly related to the amount of electricity produced by the organ. So if we can measure how much electricity is produced by our organ, we can then know how much glucose or lactate is present in the organ simultaneously. So how do we actually make our glucose and lactate sensors themselves? Well, the backbone of our glucose and our lactate sensors is a piece of carbon paper called bucky paper. Now, bucky paper by itself cannot sense glucose or lactate, so we have to add enzymes to this bucky paper in order to give it sensing abilities. Much of my research focuses on trying to find the best way to combine these glucose and the bucky paper together so that we can maximize the amount of electricity produced while also simultaneously making sure that we are accurately sensing the concentrations of glucose or lactate. That means that my research involves testing different variables such as the type of enzyme used, the amount of enzyme used, and I also tried different mechanisms of combining the the enzymes with the bucky paper. So far in our lab, we've been able to create a self-powered lactate sensor and a self-powered glucose sensor separately. And we're working on currently trying to combine these two sensors so that we can reduce the overall size of our system and reduce the cost. After we've been able to combine these two sensors together, we will then focus on adding a pump to our system, which will allow us to send essential nutrients to the organ in order to slow down the production of lactate or glucose. And ultimately, this research will help us to increase the success of organ transplants and also improve the lifestyles of those suffering from organ failure. Thank you.
Next speaker on stage is Philip Lewis. And Philip is from Ireland. He has a PhD in physiology, and he is now working as a postdoc at the University Hospital of Cologne in Germany. And the title of his talk is, Can Light Exposure Around Birth Affect Human Health Later in Life? Please welcome Philip on stage.
Hello, everyone. Yes, in Cologne, we are asking, can light exposure around the time of birth affect human health and disease later in life? You see, we all have an internal timing system that's very responsive to the daily light-dark cycle, such that it aligns our physiology with the environmental time. And you'll know this in terms of the sleep-wake cycle, but this also includes cell growth and repair, hormone secretions, metabolism, immune system function, cognitive performance, physical performance, gene expression in every cell. It's all carefully timed for health. Now, this timing system, we call it the circadian system. It operates in every cell like a clock, giving a temporal order to cellular function. And in the brain, we have the master clock, or the pacemaker, which receives the environmental time input from light receptors in the eyes, and its output synchronizes the peripheral cells so that the functions of different systems are aligned with respect to other functions and with respect to the environmental time. Of course, the right signals at the right time are good, but the wrong signals at the wrong time can be bad. So short-term perturbance of this circadian system will result in poor sleep quality, poor performance, and that can lead to increased accidents at the workplace, for instance. More long-term, severe consequences of perturbance of the clock. Research has already associated metabolic disorders, psychiatric disorders, increased susceptibility to infection, cardiovascular disease, even cancer. Now, studies in animal models have shown that the light exposure around the time of birth can imprint or program the circadian system. And we see in these animals different physiology later in life. Ultimately, this means that some light-dark paradigms around the time of birth are better than others. So we want to test if the light-dark exposure around the time of birth for humans will have an effect on health and disease. To do this, we need to look at people born into different seasons and at different latitudes, because season and latitude will determine the daily light-dark cycle. For instance, circumarctic populations may experience 24 hours a day constant light in midsummer compared to constant darkness in midwinter. In Denmark, there will be up to 18 hours of light per day in midsummer compared to only 7 hours of light per day in midwinter. And along the equator, there'll be 12 hours of light and 12 hours of darkness no matter what the time of year. So at the more extreme latitudes, away from the equator, we expect to find larger seasonal gradients in the risk of disease. And along the equator, there should be no seasonal gradient in the risk of disease. We could also group people together in terms of daily light-dark exposure metrics and see if these metrics associate with disease. Now, if we detect risks, we could probably do quite a lot about it in a very low-cost and straightforward way. Preventative strategies could include light bulbs and blackout curtains. Wouldn't that be amazing? So, to summarize and conclude, evidence from animal studies show that the circadian system may be imprinted around the time of birth, and this will affect their health later. In other words, we have supporting evidence for biological plausibility. Secondly, the associated diseases, they are highly prevalent, they have very high mortality rates, and they're very, very hard to combat. So this project in Cologne is highly, highly relevant for human health. And lastly, if we detect risks, we can then talk about low-cost, straightforward preventative strategies. That's what we're working on in Cologne. Thank you.
I'm very happy to announce the next speaker on stage, Amy Shepherd. Amy is from New Zealand. She works now on her PhD at the University of Melbourne, Australia, and her topic is how to understand the Alzheimer's disease. Please give a warm welcome to Amy.
Hi, everyone. I'd like you to please close your eyes for me just for a moment. Now, imagine walking into the room of a loved one, your mother, your grandfather, your best friend. Now imagine that as they turn to you, it's obvious they don't recognize or remember you. How do you think you'd feel? Crushed? Heartbroken? Please open your eyes. That scene is the reality of Alzheimer's disease, the slow robbery of someone's memories, what makes them truly them, all while the people who love them the most are slowly forgotten. There are currently about 50 million people around the world with Alzheimer's disease, with a new person being diagnosed every 3 seconds. My grandmother was one of those people, and so I know this disease firsthand, and watching her lose herself was incredibly difficult. So, with so many people with this awful disease, why don't we have any effective treatments? Because we don't. It's sure not for lack of trying. Over 300 therapeutics have worked in Alzheimer's mice. They haven't worked in people. There could be a lot of reasons for this, and you may think it's because the mice aren't a good model, but actually there's a rare genetic form of Alzheimer's, which is just a single gene mutation, and we can take this patient mutation and put it into our mice. And although that gene mutation only accounts for 2 or 3% of the disease, the molecular changes in the brain and the symptoms that develop are nigh identical to the much more common sporadic or randomly occurring form. Mice brains are also pretty similar to humans. It may be surprising considering they're so small, but they have very similar brain structures to us. They're evolutionarily very close. So why don't these therapeutics work? Well, we think one reason is that the way we've tested learning and memory in humans and the way we've tested it in animals has been fundamentally different. And you can understand that maybe the treatments that are working in the mice are not actually treating the symptoms we think they're treating. For example, one of the most commonly used memory tests in mice is a test called the Morris-Border maze. In this task, a mouse is placed into a circular pool of water where there's a hidden platform. And they have to find the hidden platform and then remember where it is based on spatial cues around the room. Now, for obvious reasons, we can't take Alzheimer's patients, throw them into pools of water and expect them to remember a hidden platform. But by the same token, we can't ask a mouse if it remembers who its siblings are or what it had for lunch. What we need is a common ground, a way to test experimental animals and patients in the same way to better understand the disease and if potential therapeutics could be effective. And this is what I do in my research. So I train mice to use touch-sensitive screens. They're like iPads for mice. So we can show them pictures, and the mouse will run up to the screen and touch pictures on the screen with its nose. If it chooses the correct image for that task, it'll get a delicious shot of strawberry milk. Mice love strawberry milk. So they're really motivated to get it right. Using this technique, we can take similar or the exact same tasks that we use to screen Alzheimer's in patients and give them to our mice and hopefully find the exact same symptoms. The touchscreens give us the tools we need to test our mice in a human, disease-relevant way, and then that way see if the potential therapeutics treat those disease-relevant symptoms. I believe that this will make drug development faster, less stressful for the animals involved, and more efficient. These screens are not limited to just testing Alzheimer's, they're just touchscreens. So any disease that has some kind of cognitive component, like schizophrenia, for example, which affects 1 in every 100 people, can be tested using these screens. And again, not just learning and memory, we can look at attention, problem solving, anything that your brain is involved in, we can develop tasks based on the human tasks that these mice can do. Now, the good news is that I will be publishing the start of my results in the next couple of years, which is great. But the bad news is that it takes about 15 years to take drugs from preclinical studies to the point where you'd be getting them from the doctor's clinic. So what can you and your loved ones do right now? Well, I have some good news there as well. Alzheimer's disease is highly modifiable from lifestyle interventions and all the way through your life, from early life, midlife, to even when you have the disease. It's all about having a healthy body and a healthy brain. So keep social, do crosswords, making sure you're keeping in contact with your friends, have a healthy diet, and exercise. And it's the last one that I really want to stress. We now know, based on a recent study, that you only need to do 11 minutes of moderate exercise a day in midlife to significantly reduce your risk of Alzheimer's disease. So what I'm going to ask you all to do is to briskly walk to the next train stop. Think about cycling to work. It's a really easy thing to incorporate in your life. And it's a great way to keep you and your loved ones healthy and happy into later life. Thank you very much for your time.
Our next speaker is Haizam Al-Marouki. And Haizam comes from Oman. He's a medical doctor. He works on the early detection of a disease called keratoconus. The title of his talk is therefore, How to Detect Keratoconus with a Simple Device. Please welcome him on stage.
Hello, everyone. It's an absolute pleasure being in Lindau with the Nobel laureates. Keratoconus sounds like a good buzzle word, isn't it, to use? Keratoconus. But to many eye doctors, this is a frequently encountered, visually disabling eye disease. Many eye doctors live to conquer this disease because it has a lot of, or huge burden on patients and societies. I think, though, we do have a solution. Keratoconus is a disease of the cornea of the eye. The cornea of the eye is the most front part of the eye. It's a transparent membrane. It lets light go through, as well as protecting the inner structures inside the eye. It's like the windshield of a car, basically. This cornea is normally a section of a football, or spherical and smooth-shaped. But in this disease, it becomes conical shaped, becomes like this, basically. So when light goes through, it scatters, it goes all around, and these patients have visually disabling sight. This disease has been linked to a lot of eye rubbing, as well as allergic eye disease, but these do not explain the whole story. This disease is problematic for a number of reasons. One, it's the number one indication for corneal transplantation in many parts of the world, and it's second worldwide in Germany, it's still a very important indication for corneal transplantation. Second, this disease affects people from the ages of 10 to 30 years old. As we all know that this age group is a vulnerable age group. We acquire education, form our personalities, and relationships during this age group. And we have seen a lot of patients who commit suicide with this disease. Third, these patients present to us quite late in the course of their disease, leaving us with no choice but having to transplant them with new corneas. Leave aside the many hospital visits they have to make and the complications they might get from having a new cornea. So it would be prudent to think of how can we detect this disease early in the population. At the moment, to detect the disease early, we need a large, cumbersome, and expensive tool called tomography. It costs about 80,000 euros. It's available in specialized clinics, but it's not available everywhere, and it's not available in low-income countries. But there is another simpler tool called the retinoscope. It's been used for hundreds of years in ophthalmology or in the eye diseases clinics. But no one has actually examined it whether we can detect the disease early in the population using this small, accessible, and cheap tool. It costs about a few hundred euros. The tool is very simple, actually. It projects light in a certain way to the eye of the patient, and we just move it from one side to the other. And we see a reflex doing like this. It's called scissoring reflex. So if we see the sign, it means that this patient might have the disease. If we don't see the sign, it means that this is an absolutely healthy cornea. So what we've done is we got 123 patients. This gives us 246 eyes. And so we examined these eyes with the retinoscope, and we examined them with this large machine. It's called the tomography. We were thrilled to find that we can identify 98% of these patients with this simple device. So the next step is actually to go out to the population where the disease is quite frequent. We'll go to schools, to universities where patients or where individuals are susceptible to this disease, and screen them with this simple tool. If we see the sign, we'll bring them into hospital. Now, if we bring them into hospital, if we detect the disease early, we do have treatments to stop it progressing. So if we treat it early, we don't have to transplant them with corneas at the end of the day. Thank you so much.
Our last speaker is Miriam van Dijk. And Miriam comes from the United States. She's currently doing a PhD in epidemiology at the University of Atlanta, Georgia. The title of her talk is Race, Place, Class, and Heart Diseases. Please welcome Miriam on stage.
Hello. I'd like to begin my time with you today by asking a question. Does race, place, and class impact health? And I ask this question because where I live in the United States, as well as many countries around the world, the distribution of health is patterned by those three factors. Race, which can be thought of as the color of one's skin, place, which is where you live, and class, which can be determined by how much money and education you have. And in my area of research, heart disease, those three factors are important. Heart disease is the leading cause of death in the United States, as is the case in many countries, including Germany. In my research in the United States, we have observed that heart disease death rates have decreased over time, which is good, but there are still differences by race and by place. For example, in 2015, African Americans had a 21% higher rate of heart disease deaths than whites in the country overall. And when we looked at this across states, we saw further differences. For some states, the difference between African Americans and whites were larger than for other states. For other states, there were no differences. And for a few states, African Americans had lower rates of heart disease deaths than whites. Well, why? Why are there differences by race and by place in heart disease in the United States? What is it about the race a person is assigned and the place in which people live that could impact their heart health? And while some believe that genetic factors are important for racial differences in the US, and surely they are for the development of heart disease, evidence to date points to a person's environment as the primary reason for racial differences in heart disease. And so another area of my research focuses on finding factors in a person's environment that can contribute to racial differences. So I researched discrimination as well as social policies. And today I'm going to focus on social policies. And for that, I'll start at the top. And what I mean by the top is that there are overarching policies that impact the health of a country, of states, of communities, which are made up of individuals which have organs, tissues, and cells, right? And so with that in mind, I researched minimum wage policy in the United States at the national level and across states. And minimum wage policies created by governments to ensure that workers are paid at least a minimum amount of money per hour for their work. So in Germany, the national minimum wage is 84 euros per hour. In the United States, the national minimum wage is $7.25, or about 6.22 euros per hour. However, there are some states that have chosen to increase their minimum wage above that $7.25. For example, California has a minimum wage of $11 per hour, or about 9.44 euros. And in my research, I have found that states that have chosen to increase their minimum wage have, on average, lower heart disease death rates than states that have chosen to maintain that national minimum wage. On the surface, this makes sense. Research has shown that individuals with a higher income have better heart health. And while I'll continue to explore this research topic, perhaps increasing the minimum wage can positively impact heart health. In summary, my research in the US has shown that African Americans have a higher rate of heart disease deaths than whites in the country overall, and for many, but not all states. In addition, states that have increased their minimum wage have lower heart disease death rates. In closing, I would like to leave you with two questions. The first, what are social factors in your own community that impact health? As I have mentioned in the US, race, place, and class are important for heart disease. Second, what are some solutions that can help close the gaps in health between groups across a population? Based on my research, it's possible that if we increase the minimum wage, we have better heart health. As you go about your day-to-day lives and improve the world in your own way, I hope you keep those two questions in mind. Thank you for your time.
So this was Campus Talks. You can experience the fascination of science in two different ways. In front of the TV screen, like now, but you can also go on our webpage where you can watch all the talks that have been recorded, or you can download them as podcast. So I say goodbye and see you next time.